My name is Francine. I'm a security architect and I work at View Group IT. Here all the way from sunny Kristiansand, well, ish sunny at least. And today we are going to be talking about protocol hopping C2. So what we have on the agenda is the way we normally think about C2 and instant response when it comes to C2, so command and control that is. The architecture behind it, which is core versus transport adapter. Then we'll have a tiny demo, which was, it's extremely simple. You know, I'm not the creator of Cobalt Strike, so it's very simple. We're going to be talking about defensive implications for detection and instant response, and some trade-offs and limitations of that architecture. So the guiding idea of this session is that transport disruption does not actually neutralize command logic, it just disrupts communication, degrades communication. So we're going to be looking at what to expect from containment, how containment differs from eradication, and so on and so forth. So it's important to note what this talk is and what it isn't. So it is a mental model correction about layers and where we operate in terms of detection. It is an architectural pattern, which is we have a stateful core and we have adapters. We have the different ways of transporting the C2 traffic. It is a simple demo. Again, very simple, you will see that. And so pragmatic implications for the defenders. So this is not a deep dive into like stealth and exploit. This is not a tutorial. This, again, is not a deep dive into Cobalt Strike. This is not anything that fancy. So it's not a claim that the endpoint detection response is not efficient anymore, because it still is. It's just, it's a different view on it. And it's not a novelty claim either, because this pattern has been known for, well, quite a while now. So if we have a look at the slide, so how we see this whole situation. So our pattern normally is to block known bad domains, to sync all outbound DNS to non-corporate resolvers, kill HTTP or HTTPS beacons whenever we see them, so we whitelist egress points, and so we break the channel in instant response as the first kind of thing that we do, as the first step in our process. So what can go wrong is that if we treat the protocol as the entire system, if we treat a protocol as, okay, if we break this, then everything stops suddenly, then we might disrupt it and mistake it for eradication. So with transport-agnostic or protocol hopping C2 traffic, the intent is the same, exfiltration of data or whatever it might be, and it continues via a different channel, as we will see again. So the containment looks like we've eradicated the problem and the state still persists. So the problem is still there, the threat is still there. But we kind of think, oh, well, that's great, we can close the case in instant response. And the focus shifts to a completely wrong layer. So just a small kind of throwback, throw-in, whatever, for people not fully familiar with C2. So it is basically a communication channel between a compromised host and an attacker after the initial compromise. So it is bidirectional, which means that, the host can send the data to the controller. The controller obviously receives the data, and so on and so forth. It supports remote tasking, so the attacker who's in control of the system, the command and control system, can actually get what they want, so they can run the tasks, execute processes. It is about result reporting as well, so the state of the system will get reported to the controller, and it is persistent. So basically it can be said that without command and control, an attacker has a breach. So they have that. With command and control, they have persistence. So what does it do? It just enables the attacker to control the host and coordinate actions on that host after the initial compromise. So task distribution, data exfiltration, which is like a very big proportion of that. Host management, operation control, so scheduling tasks, for example, and coordination across multiple hosts as well. So the two nutshells, so the operational architecture of it and the practical reality. So it turns a compromised host from a one-time breach into a remotely controlled asset. So when command and control, like I said, it's persistent. So when command and control is present, then that means that the attacker can actually come and go as they please. So conceptually, it contains two parts, which is the command logic, stateful core of the thing, which decides what happens next. So it queues tasks, it schedules tasks, it tracks session state, and then there's the transport mechanism, which is basically how it moves the messages, how it moves the bytes from the host to the kind of command center. And yeah, there can be the most used protocols are HTTP, HTTPS, and it's DNS and all sorts of custom protocols. So most of it kind of looks like beaconing, which is infected host checks in with the controller at intervals, and operator replies only when work exists. So it's not like it generates noise all the time. It shouldn't, at least. And yeah, the typical observable patterns are regular outbound callbacks, small requests, larger response with data exfiltration specifically. Yeah, and normally command and control adds jitter, which is kind of like randomness in timing of the call and response. So instead of, for example, sending data every 60 seconds, it will do 45 seconds, then 72, then 120 or something like that, so to be less kind of detectable in that regard. So the key idea here is in this talk, is to separate the command logic from the transport itself. So the core holds the session state and scheduling decisions. Adapter implements protocol-specific input-output, so it basically decides how the bytes are going to move. And the failover becomes an engineering feature. So if something gets disrupted, one of the protocols gets disrupted, then yeah, it fails over to something else. Once again, we'll look into it. So the components, as you can see, are the core, which is something that tracks the state, the intent, and so yeah, session, task queue, and scheduler. Then we have the pluggable adapter, which selects which protocol we're using for transport. And yeah, you can see in our case it's going to be DNS-like kind of UDP traffic. If we look at the polling cycle, that happens normally in those things. So we can see the poll and response. So nothing really is built into it for resilience, for example. Now, if we look at the polling cycle with failover, we can see that if the transport becomes unavailable, there will be a failover decision. The poll function will try to access an alternative adapter, and then response will continue. So the real-world example would be beacon transports like Cobalt Strike, again, so it has supported multiple communication protocols for quite a while, including DNS-based variants and different versions of custom protocols. So the point here is not the tool, because, like I said before, it's not a novelty thing. It's more of a kind of mindset shift towards where and how we detect things. And hybrid approaches use one channel normally with C2 to check for work, and another channel for data and data exfiltration and manipulation or whatever. So transport switching is common in networks. So it's, yeah, again, nothing really brand new. So blocking one protocol will remove mostly just one adapter. So the state will remain the same, the intent will remain the same, the scheduling will continue. The behavior may remain beacon-like across all transports, but the containment decisions might kind of go in a different way, because we will think that, oh, okay, so that is eradicated because there's no more HTTP traffic, for example. So it needs to be validated. Whenever we disrupt something, we need to validate that actually we have eradicated things, not just contained one part of the process. So next time we're going to look at the demo. What we're going to see is the healthy polling via HTTP. Then we are going to simulate the disruption, which is, yeah, we're going to disable HTTP and see what happens then. we will see that the agent, hopefully if nothing breaks, will fail over to DNS-like state. Then we will look what happens to session identifier. Clues there, it should remain the same. And yeah, then we will see what happens if we restore all the transports. So again, this demo is not some novelty thing. It's not Cobalt Strike v2. It's there are no exploits, no persistence. It's just architecture plus failover mechanics. So first, we are going to look at this. Yeah, everyone can see that? We can see the interaction between a controller and the agent. So yeah, you can see that the message being output is, yeah, hello from the controller. So as we can see, everything is going via HTTP. Everything is fine. Now let's imagine that we are containing HTTP. So we're disabling it, and now we see that our agent fails HTTP and fails over to DNS. So now it's going to communicate all the data that is trying to exfiltrate via DNS. So then we notice that as defenders, for example. And then we disable DNS as well, for whatever reason. So it times out, it tries, so the core logic kind of tries 3 more times, and it fails over to the next transport, in which case, in our case, this is ICMP. Again, this is very, very simple, so like, yeah, nothing real is happening here. But yeah, so this is basically what we have. Now, if we kill that as well, the agent will continue, actually, with polling everything and trying different ways to reach the command and control kind of core. So, but nothing is happening really. But the thing is, the state still persists. So it will continue going on and on and on until, for example, Jenkins in accounting needs HTTP, for example. So we enable that, and now the persistent state detects HTTP. And please, yeah, there we go. Now it works. So the whole point of this is that we have persistent state. So when we killed the HTTP, for example, it just failed over to another thing. The session ID remained the same, everything remained the same, the intent remained the same, and the infiltration, or exfiltration rather, was just lying in wait, basically. So it was expecting something to happen. Because, well, the thing is, we cannot isolate hosts normally forever, because something needs to have access to the internet. For example, we need DNS, we need HTTP, we need all sorts of things for updates, whatnot. So if we just kill the transport, then, well, okay, we've kind of contained it, but the core is still there. So yeah, as we've seen, so protocol semantics changed, the protocol itself, visibility and inspection surface. So for example, if we don't have HTTP traffic anymore, then it's like, oh, okay, well, I guess that's fine. And the network indicators, they've changed. What didn't change is session ID, session state, the schedule intent, the overall intent. So like, okay, what are we doing? What is this tool actually trying to accomplish? So the operator workflow and logic didn't change, and the containment risk actually shifted from we have an active incident to we're kind of done here. And so this is the false sense of security. So why are we talking about all of this? This is to kind of shift from detecting the port and detecting the protocol into detecting the behavior itself. So signals that can survive transport change are the beacon-like periodicity, which is also can be kind of like altered a bit with jitter. So repeated contact to a single external destination set. So state continuity, that all of that can survive a transport change because this is going to be persistent. So that means that if that is the only thing that we're focusing on. So the protocol, the network kind of layer detection, it's not really sufficient. So we need to layer our detection layer, our defenses. So we need to use network and endpoint telemetry together, and we need to validate eradication at the host level. So, like I said, if we just see that there's no traffic, it means that maybe that thing is still persisting, but it's just not pulling anything. So a practical checklist for that would be, and I'm saying this again and again, is assuming that if we kill some transport, we need to assume that it is degraded and not gone, it's not eradicated. We need to confirm endpoint state. So is there a persistence? Are there any scheduled processes running? Are there any scheduled tasks? Are there any injected threads? So we need to look for alternative egress paths or fallback beacons, if anything is present still. We need to measure the timing also. So does the pattern reappear somewhere? Is there anything dodgy going on? And also we need to document our containment, which means like, okay, fine, so what have we done, what haven't we done, what have we seen, and we need to verify everything post-containment and post-eradication explicitly. So our trade-offs and limitations are basically the failovers in those kinds of protocol-agnostic tools. They obviously increase noise and they increase detection surface, which means that, I mean, DNS is pretty noisy on the network in its own right. So that is the first thing that we are going to see, but that is still not enough. And we need to concentrate on the things that we see apart from the kind of like this small amount of traffic that repeats itself. And yeah, so why are we talking about this? Again, so it clarifies what containment actually accomplishes and what happens in those protocol-agnostic, protocol hopping things. And it prevents the overconfidence during our incident response. It prevents us from closing the incident response way too early when we see that something stops. And it encourages layer-appropriate detection and design. So our key takeaways is, I kind of get the feeling that this session is going to be really short. So treat transport disruption as a degrading action. We need to model command and control as a system, if we're doing that. So that's a core state plus adapters. And we need to defend across layers. So behavior plus endpoint correlation plus network context. So the fact that it is transport agnostic does not mean that it is detection proof. Actually, it's quite the opposite. So we are talking about a resilience pattern that changes assumptions. There we go. Thank you. Questions? I don't really have anything else for you guys. So, I mean, I can run the tool again. It's pretty. It's got colors. So I mean, we've got quite a lot of time. So I'm gonna be hanging around here for a while. So yeah, can shake your hands.